is our last class. Yeah. So how are things with you guys? Aspect of electric powertrain. I mean, so does electric powertrain have emission? So it'll have to be hybrids to actually to be able to actually talk about emission gases, right? So today we're going to I'm going to introduce you to control of PHEV plug-in hybrids for emission reductions. So this is only one lecture that's going to cover a lot of stuff. So and I don't expect you to understand all the details, but I still want you to have like I've been telling, I want you to have some idea and some introduction to how the system works, including the internal combustion engines and what type of problems there are when it comes to emission problem for hybrids. Okay. So the overall approach, by the way, this was also part of my thesis. So this is relatively old work, but this was one of the first work that actually dealt with tailpipe emissions instead of engine out emissions. So we'll also talk about that too. So again, this is a control problem, and the flow is very similar. So we need to first develop a model, not just the powertrain model, but including the emission model, and then just like we have been doing, we wanted to. I wanted to use dynamic programming to be able to find the optimal solution, which can give you, full potential of the given system, and we might be able to get some insights from and strategies, optimal strategies from the DP results, and then we can also see performance limits. Okay. And then the last part is going to be to actually design real-time controller based on these studies. Okay. So this is very important slide. So for you to understand. How tailpipe emissions are created or generated. So right out of the engine, we have this exhaust gas pipe, and we will have exhaust gas flowing out of the cylinder and flowing into this exhaust pipe, and that's going to go through this catalytic converter, which converts harmful emissions into unharmful emissions, such as CO2, H2O, and nitrogen. Okay, but what you get directly out of the engine, you contain those exhaust gas contains harmful emissions such as NOx, NOx, NO and NO2, and so forth. And then there's CO, which is also harmful for human. And there's also, I think, NOx, CO, and hydrocarbon. Okay. So for gasoline engines, you have those three harmful emissions. And luckily, really smart people back in, I think, 1980s, something like that, came up with this catalytic converter that converts these three harmful emissions into safe, unharmful emissions. So that was a breakthrough. So you don't actually, you don't actually smell these or inhale these harmful emissions out of the tailpipe emissions. But that's under the condition that this catalytic converter is activated. What that means is this is also called a three-way catalyst because it converts three emissions. And this converter is only activated when it's hot enough. Okay. So what that means is when everything is cold. So when you start the engine in the morning, you have cold engine and you have cold converter. Everything is cold. And at that time, this converter is not activated. It doesn't work. It doesn't convert. So during that time, all the harmful emissions coming out of the engine directly flows out to the tailpipe. Tailpipe end part. So I don't know if you guys have these experiences, but in the morning, especially during winter times, if you go to a parking lot, you smell this very gaseous exhaust gases, right, in the morning. And that's because every vehicle is emitting this harmful emissions, especially hydrocarbon has this smell. Okay. So the goal of engineers back in 1990s and still, they are trying to warm up this converter using minimum fuel. Okay. And meaning that we want to activate this converter as soon as possible. Okay. How can we activate this converter? Well, we want to warm up. We want to make hot. We want to make this converter hot. Okay. How can we make converter hot? Any guesses? I think it's straightforward.
Electric warming.
That's a possibility, but that requires extra component cost and requires electricity. But it's possible.
Can we use engine heat loss?
Yes. So in the past and still, the most efficient and cost-effective solution is just simply using hot engine exhaust. Okay. engine exhaust is hot. So if you just let it flow through the converter, then converter becomes hot and it starts to convert these harmful emissions. Okay. So that's what has been happening over the last few decades, and still do that. But if you warm up converter using exhaust gas, then it'll take some time to activate the converter, right? And especially if you want to warm up converter faster, then what should you do? Well, you want to flow hotter exhaust and more exhaust. Gas flow will make converter activate faster. But if you do so until the time you activate the converter, you are going to produce more harmful emissions, right? So you need to somehow optimize, how to warm up, how to activate this converter, right? So if you look at this right figure, okay, this is a very good figure, very informative figure that shows what's going on, okay? So this is cold start, and what this means is this one means, hot engine out emission, okay? So if something is lower than 1, then you're converting the emission so that it's lower than the hot engine out emission. If something is higher than 1, then it means you're producing more emission than the steady state hot engine out emission. And this can happen because when you start the engine in the morning, when everything is cold, the engine is also cold. And if you have, if you do cold start, then the engine out emission will contain more harmful emissions. Okay. By the way, X is time. Okay. So initially you have about 2.4 more emissions, harmful emissions. Moreover, the converter is not activated, so all of the engine out emissions directly flows out to the environment, okay, without any conversion. And as engine starts to warm up, this engine out emission slowly decreases. And then all of a sudden, this converter is now activated, okay? Meaning that it starts to convert harmful emissions into safe emissions, okay? And then, boom, you can see that this dramatically drops. The tailpipe emissions, harmful emissions, dramatically drops and then stays there. Okay, but note that engine out emission is still high during this time. Okay, so the tailpipe emission is very important. and it's the key to reduce this harmful emissions. Okay, is everybody following? Any questions? This slide is very important. It gives you, what's happening in the after treatment system. Usually, this whole thing is called after treatment system. Okay, and you're looking at some dynamic behavior with temperature increase with engine and converter, and as soon as converter becomes active, then the harmful emissions are now converted into safe emissions. So when engine is hot and converter is hot, you only get this much of tailpipe emissions, okay, harmful emissions. Safe emissions. So you have all the gases are safe emissions, and harmful emissions are very small. Okay, but initially you have this much of harmful emissions. Okay.
Can I ask a question?
Mm-hmm.
Why does engine out emissions decrease exponentially?
With temperature increase. So in the morning, everything is cold, right? It's called soaked, right? Everything is same temperature as environment. And as soon as you start the engine, you have this combustion inside of the engine. And that combustion is going to start warm up the engine, right? When engine becomes warm and the cylinder wall becomes warm, the engine out harmful emission decreases. Is that understandable?
그러면 불완전 연소 하던 게 완전 연소해서 그런 건가요?
그런 측면도 있죠. 네. So to explain why that's happening, you need to take internal combustion engine course, and it's all about thermodynamics. But two major cause is incomplete combustion and dissociation. So and that's, I think, outside the scope of this course. So it's electric, so it's chemical reaction and thermodynamics, and due to the cylinder wall temperature, the amount of harmful emissions changes. So when everything is warmed up, it reduces.
Thank you, Professor.
Yep. And so that last slide was about how conventional after treatment system works. Okay, to give you an idea of how it works, right? For gasoline engine, okay. For diesel engines, it's more complicated, but conceptually similar. And the problem we are facing is that when we electrify our powertrain, such as hybrids and plug-in hybrids, I mean, if you go to pure battery EV then you don't have an engine, so you don't have to worry about these harmful emissions. But when you do have engine, you do need to worry about these things. Okay. And now let's imagine what's going to happen when we have hybrid powertrain. Okay. Now you have, especially when it comes to plug-in hybrids, it can be quite interesting. The problem can be quite interesting. So please take a look. So so take a look at this. So PHEVs may produce more emissions than conventional HEVs because PHEVs are designed to reduce fuel consumption by frequent and extended engine shutdown. So what that means is engine is not frequently used. Engine is rarely used. So if you go back, so if you use engine rarely, what's going to happen? If you turn the engine off, then everything is going to start to cool down, right? Including converter. Okay. So let's say you started the engine, okay? And then and first time it's going to be a cold start, right? So everything is cold. So you emit a lot of harmful emissions initially, right? But then because this is PHEV, you don't want to use engine. So battery kicks in and you shut down the engine. So you rarely use engine. So the converter just started to activate, okay? But then if you shut down the engine, now temperature will start to come back down. And now next time you start the engine, it's going to be another cold start. Everybody following? So that's what's happening here. So this black dot is engine on operating point. And so this is drive cycle. And this is fuel consumption rate. So because this is PHEV and you have a large motor and battery, you don't have to use an engine unless your motor and battery cannot provide the demanded power, right? So if the engine will come on only if a driver asks for high power, right? And that's this region, right? But for a very short amount of time, okay? And because of that short time, the catalyst converter rarely activated. Okay, I think the activation temperature is something like 500 K. So that means aftertreatment system is never activated. So whenever you start the engine, it's cold start. So compared to conventional powertrain, harmful emissions are more emitted, okay, than just conventional powertrain. this is counterintuitive, right? People might think that it's cleaner, but unless you control this properly, you can actually create more harmful emissions. Okay, I mean, for safe emissions such as nitrogen, water, and CO2, those are not generated a lot because you don't use engine. But we are talking about this harmful emissions, which small amount of harmful emissions can actually toxicate your body. Okay, can actually harm your body. Okay. And the irony is that if you don't control properly, PHEVs can produce more harmful emissions than conventional powertrain because converter is never activated. Okay. And you can also see that data from in the old days. There was this a company who actually modified Prius, turn a hybrid Prius into plug-in hybrids without proper engineering for the control. Okay, and what happened was that because you have bigger battery and you can use more electricity from battery, fuel economy will be better, right? But tailpipe emission actually increased. Okay. So just factory Prius, just right out of the factory, OEM, Prius had this much of emission, but then when you put bigger battery and use more battery and less engine, you actually created more emissions. And that's because this was not engineered properly, right? So the problem, the motivation was this, and the problem we were trying to tackle here is that how can we control properly so that we can also minimize emission. We can take care of the emission, not just fuel economy. Okay. So we started with modeling. So we use all the same model we have been using, same target vehicle, P2 hybrids, same components, same target vehicles, but we needed this emission model, okay? And to be able to model, to be able to compute tailpipe emissions, we need two things. First, we need to be able to compute these emission outputs, emission flow, how much emissions, harmful emissions coming out, and then temperature, engine temperature. And then we also need this three-way catalytic converter model, which computes catalytic converter temperature, and tailpipe emissions. Okay. So this is the new model, in addition to the model you guys have been playing with. In addition to the power train model you have been playing with, we need this additional model, which is the basically engine thermodynamic model, and then after treatment dynamic model. So from the quasi-static engine model, we have been only computing torque and fuel consumption, but now we need to compute these three. And we can get these numbers from experiment test data, just like engine map. Okay, so we can get these, but these numbers are assumes when engine is hot. Okay, so we need to somehow be able to compute, calculate a cold start engine, right? So this engine thermodynamics does that part. So engine thermodynamic model computes temperature, engine temperature, and then computes correction factor that corrects this hot temperature into cold temperature and hot flow rate to cold flow rate, and so forth. Okay. By the way, it was very challenging. It was very challenging to model a single lumped engine temperature. So instead, what I did was approximate engine temperature using coolant temperature. Okay, assuming that coolant temperature is a representative temperature for the engine. Okay. Well, engine temperature has this distribution. You know, cylinder has high temperature, but engine block has, you know, some gradient. Temperature is different at everywhere. But for modeling purposes, we needed one state that can represent engine temperature. So I thought coolant temperature does that kind of job. Okay. Meaning that they go together. Engine temperature and coolant temperature move together. Okay. And then, so by doing that, we can calculate corrected or cold engine outputs, cold engine emissions. And after treatment model takes those values and try to model the thermal dynamics of the converter, and finally we want to be able to compute tailpipe emission using conversion efficiency map. So this conversion efficiency map is a function of converter temperature. Okay. But this has this feedback mechanism, because when converter converts converter converts these emissions, it produces some heat. Okay. So that's a quick summary of the after treatment system. And if you look at the if you look for state variable, dynamic states, we have two dynamic states, coolant temperature and catalytic converter temperature. And cool, so this is more details, okay? So I basically explained all of these very conceptually, okay? So this is coolant temperature dynamics. So this is nothing more than heat transfer model. If you're a mechanical engineer, you should be familiar with this. This is simple 1 degrees of freedom heat transfer model, except for this part. So when coolant becomes too hot, then the cooling system starts to work, and the coolant temperature is maintained constant. Okay, usually about 90 degrees Celsius. And then there's correction factor that corrects hot value into cold value. Okay, if it's cold. So as you can see, when coolant temperature is cold, you have some correction values. Okay, it's either amplified or reduced. Okay. Including fuel consumption. But as engine gets warmer, this correction factor converges to 1. Okay, meaning that now it becomes hot values. Okay. And then this is converter temperature dynamics. Again, this is a heat transfer model. So this is the resulting heat transfer model. But then we have this converter heat generation part. So we have that feedback mechanism. And then we have this conversion efficiency map, which shows that once converter temperature hits about 500 K, the efficiency approaches 98%, 99%, which means all the harmful emissions are converted into safe emissions. And we need these maps for hydrocarbon, CO, and what's the other one? What's the third one? Hydrocarbon, CO, and NOx. Yeah. So this is the model validation. So we compare the model with test data provided by General Motors. You can see the overall trend is similar, especially hydrocarbon. Hydrocarbon shows very similar behavior, but CO and NOx show some discrepancy for some reason. Maybe the test data has some error, or modeling does not quite reflect the reality. Okay, so here there is some discrepancy here and here, but hydrocarbon shows pretty good, similar model. Oh, by the way, this one, left one is a converter model only, and the right side includes the complete model, meaning that the engine correction factor and coolant temperature model is also included. Okay. So it's time for dynamic programming. So hopefully everybody is now familiar with dynamic programming, right? So everything is same, but there is some difference. First of all, we introduced emission in the cost function. And we have now converter temperature. Okay. By the way, we had two dynamic states, right? Coolant temperature and converter temperature. But when I formulate the dynamic programming problem, I decided to remove the coolant temperature and relate coolant temperature with converter temperature, because converter they actually show similar behavior, plus converter temperature is the dominating factor when it comes to tailpipe emission. So there was one major approximation to make DP computable. Okay. So when I was a student, I had I had access to like 4 computers. Each computer had 4 cores. So that was like, I don't know, 12 years ago. And I was using 4 computers with 4 cores each, and I was able to use 3 Matlab running on each computer. And when I was running for fuel economy optimization, I could do it in like, I don't know, like 30 minutes, something like that, 1 hour, less than 1 hour, using 1 computer. But then when I moved to this emission problem, now we have extra state. So curse of dimensionality comes in, and even if I remove the coolant temperature, I needed 4 computers, and I still am running three Matlabs each computer, and it took me about 5 hours. 5 hours to run this in parallel computing. Okay, maybe today's computer, I just need 1 computer to do that job. I don't know. Anyway, just to give you an idea of what I also had to go through when it comes to computing. That gives you some idea of how much computing load we need, when we have a larger problem and try to solve that using DP. So that's like 12 MATLAB running simultaneously. Anyway, so this is DP problem, and then this is the results. So now we are interested in emission, hydrocarbon, and we wanted to see, so here's the hypothesis, right? So if you only focus on fuel economy, engine will not be used often, right? Engine will be minimized, engine usage will be minimized, but that's going to create this emission problem. So to make sure your converter temperature is hot and readily available when you start the engine, from the emission perspective, you need to consume more fuel, right? Because you need to use more engine, okay? So maybe there is a trade-off between fuel economy and emission. So that was hypothesis, and this results clearly shows that trade-off, okay? So what this means is if you make beta equal to 0, so if you neglect emission, then your fuel economy is minimized, right? Optimized. But as you increase beta, which is this term, right? And as you increase beta, hydrocarbon substantially decreased, but fuel consumption is increased, right? But this is in the case of 20-mile distance. By the way, this the target vehicle has all electric range of 20 miles, meaning that you can travel 20 miles without using engine unless power demand cannot be provided by the motor, okay? So that's why this trade-off is quite significant. But when it comes to 30 miles distance, the trade-off is reduced. And that's because you already have to use engine more frequently because of the longer distance, okay? So you still do see this trade-off, but less obvious, right? And let's take a look at detailed trajectory response for these 4 designs, okay? Beta equal to 0 and 500 in these 2. So in the case of 20-mile, solution, this is DP solution, okay? This is direct DP raw data, okay? And it shows that when beta equal to 0, you know, the DP does not care about emission, and catalytic converter is never activated. The activation temperature is called light off temperature, okay? And it never goes beyond this value, okay? But if you look at this beta equals to 500 solution, the DP tries to maintain higher temperature, okay? So that total hydrocarbon is reduced because converter is activated. It's warmer, okay? But that's at the expense of using more engine and more fuel, okay? If you compare this part, you can see more fuel consumption there, okay? Let's take a look at 30-mile case, longer distance. Like I said, even if beta equals to 0, even if optimization cost function does not include emission, you already have to use engine because you don't have enough energy from the battery. So you can see converter temperature, it stays above light off temperature because you have to use engine. But if you increase beta to 500, DP make sure converter temperature stays well above 600, so that conversion efficiency is always close to 100%. Here you have these areas where conversion efficiency drops. Okay. Can you guys see what's going on? Any questions?
Does the engine, I mean, SOC also falls to the...
I think now the slides have a lot of details, you know, how, so this is analysis of the DP solution, but I think this is a bit of too much details for you guys at this point, and we don't have much time. So I'm going to move fast for the rest of the slides. I think if you understood what I have been discussing so far, you should be fine, and you're still good, and you're understanding the key problem involved with electric powertrain, hybrid and plug-in hybrids. You do need to care about emissions, not just fuel economy, okay? And if you have some understanding of how after treatment system works, then you're good to go, okay? But we still can do, you know, DP-based, DP, you know, control strategy extraction from DP, just like we have been doing. And same applies. I apply the same concept here. And but because this is plug-in hybrid, I introduced this new concept of energy to distance ratio theta, which determines which can give us some information about how much battery energy we have compared to how much distance I have to travel. So that way we can sort of adjust our control strategy, how fast we want to deplete the battery. Okay. So this is so this is something new for plug-in hybrids, so that we can control. We want to maintain. We want to maintain a state of charge, or do we want to deplete SOC as fast as we can, or do we want to deplete SOC slowly? We can control these things, right, using this new variable called energy to distance ratio. So that was something new, and then I also so when it comes to extracting DP solutions, I used two variables, okay, that we didn't talk about before. That is this energy to distance ratio, theta, and converter temperature. Okay. So now we can extract this on-off, engine on-off map, and gear shift map, and then power split ratio map from DP solutions. So we did this before, but here what's different is that we extract this as a function of theta, okay? Theta bar is normalized theta, so it varies from 0 to 1, okay? And this is the results, and you can take a look at these details, but the key here is that if you look at this, when theta equal to close to 1, then this is charge sustaining. Okay. When theta equal to close to 0, then this is EV. Okay. So meaning that we want to deplete SOC fast for EV case, and we want to maintain. I'm sorry. It's the other way. So this is EV. This is CS. Sorry about that. So when theta equal to 0, then we need to maintain SOC. So you can see this is very similar to the hybrid solution. Okay. But with increasing theta, we want to now deplete SOC, deplete battery SOC. So what's happening here is that you can see that this engine on-off power threshold value starts to increase. Can you guys see? So this increases, okay? If you think about it, this is obvious, right? If you want to use more battery and motor, you should less engine, right? You should use less engine. So what this means is for low power region, use motor and battery, right? And that threshold value increases with theta. Okay. And this is just one results, which is engine on-off strategy. And if you look at So the conclusion is that engine on-off strategy must be adaptive with respect to theta bar. Okay. And if you look at shift strategy, we also can see some change with increasing theta. But power split ratio strategy doesn't quite change substantially. What's changing is the operating points on this line, okay? And that's because of the engine on, that's because of different engine on-off strategy and shift strategy, okay? But these operating points still lies on this line, okay? It's not like it's operated here. Okay, and then, so that was hot results, meaning that we didn't really care about converter temperature. But for cold to start control strategy, we need to somehow analyze how DP operates during cold start. So we included this converter temperature and see how these strategies change as a function of converter temperature. So the method is repeated. Okay. Now this control policy, DP policy is now three-dimensional because there's a converter temperature and time K. And so what you're looking at here is cold start. Okay. And so you're looking at how control strategy changes when converter is cold. Okay. So what this tells us is that when converter in engine is cold, we should use different control strategy. So this is different from the hot strategy. Okay. So please take a look on your own. We have time running out, so I'll have to move fast. So you do see some different strategy compared to hot strategy. Okay. So and in summary, it tries to keep the engine exhaust gas hot temperature higher. Okay. To maintain converter temperature hot. So this is the real-time controller that was proposed back then. So now it's a function of two things: theta, because it's PHEV, and then there's a temperature side. Where is So yeah, this slide shows that cold start strategy. Okay. The key is the engine stop start. So this is quite different from hot strategy. Okay. The time is up for today, so I'll have to wrap up here. But if you're interested in emission control, please take a look at this lecture notes, and questions are welcome. Okay. So